This is chi-square part 3. Okay, now I'm just doing some problems straight from the book. This is like example number 6 on page 693. This is example number 14 on page 694. And then next up is an AP Statistics for Response question. Okay, so just more practice looking at chi-square problems and getting used to answering them. Okay, let's begin. Casinos are required to verify that their games operate as advertised. American roulette wheels have 38 slots, 18 red, 18 black, and 2 green. In one casino, the managers record data from a random sample of 200 spins of one of their American roulette wheels. The one-way table below displays the results. Color, red, black, and just a couple green. Confirm that the expected counts are large enough to use a chi-square distribution to calculate the p-value. What degree of freedom should you use? Are my expected counts large enough? Okay, for my expected counts, I need to do my sample size times my probability of the value of the red result on the roulette table. And so 200 times 18 over 38 is 94.73. 200 times 18 over 38 is 94.73. And 200 times 2 over 38, because there's only 2 greens on the roulette wheel, is 10.53. Okay? 18 black, 18 red, and 2 green. All of these expected counts are greater than or equal to 5, so the large counts condition is met. And my degree of freedom is categories minus 1, which is 3 categories, minus 1, which is 2. Sketch a graph of the chi-square statistic that shows the p-value. So my chi-square statistic is observed minus expected squared over expected. So that's here. I did all 3 components showing work. And then I got these 3 components, 1.0, 0.19, and 2.8. I got a chi-square value of 4.3. This is always right-sided. Okay, but remember that your alternative hypothesis is written as two-sided, but chi-square by nature is designed to just be a right-sided, right-shaded, right-skewed distribution. Okay, so there's all my chi-square values here, and it's just to the right of the 4 and shaded to the right. Fun facts, your p-value is your mean minus 2, and your p-value minus 2 is the peak, which in this case is 0, because my degree of freedom... I'm pretty sure this is supposed to be degree of freedom minus 2. Okay. Degree of freedom minus 2 is the peak, and that would be 0. So degree of freedom was 2. 2 minus 2 is 0. Okay. Use table C to find the p-value. Then use your calculator's chi-square CDF command. Table C, your p-value is somewhere between 0.10 and 0.15. On your calculator, chi-square CDF, lower, upper degree of freedom, gives you 0.133. And 0.13 is between 0.10 and 0.15. What conclusion could you draw about whether or not the roulette wheel is operating correctly? Justify your answer. Because the p-value is greater than alpha, we fail to reject HO. We do not have convincing evidence that the distribution of outcomes on the roulette wheel is not what it should be. Okay? Because even though we didn't write them out yet for this one, our null hypothesis is always that there's no change, that we're not going to bring down the casino, okay? That the roulette wheel is working correctly, kind of like your equal sign and your HO, okay? All right, so the roulette wheel is working correctly, that the observed is somewhat equal to, close enough equal to your expected, okay? And then our HA would mean that our roulette wheel is not working correctly. The observed counts are not close enough to the expected counts. Okay, another one. Page 14, number 14 on page 694. Is your random number generator working? Use your calculator's randint feature to generate 200 digits from 0 to 9 and store them in a list. So if I went to my calculator, I could do this and I could go math, probability, option 5, randint, and I could go from 0 to 9. I just use my comma. From 0 to 9, and what's the rest of that? 200 digits. Okay, close it up, and oh yeah, I need to store this into my L1. Store in my, I could just hit second L1. Okay, enter. Okay, and there they all are anyway, but I think it's a little easier to look at them in here. So here's my L1 and here's all 200 digits. So one thing I can do is I can look at the number of times I have a 0 and I can count 1. Well, I should start at the very top. Okay, 20th digit, 10th digit. Okay, that's the top, my first digit. So I can scroll through this and count how many times I have a 0. Oh, here's another thing I can do. List, sort my L1. Okay, oops. Okay, list, sort my L1, enter. Okay, stat, edit. I can look at my L1 now. Okay, I had 21 zeros, which is obviously different than I had this other year, but I can see how many zeros I had. Then I can see how many ones I had, and then I can see how many twos I have, okay? And I can fill in this chart of observed counts, or I can just look at these values from this other year. Okay, so here's all my observed counts of each of the digits in the random digit generator from 0 to 9. And then here's my expected counts. Because I did 200 digits and I have 10 digits, I would expect 20 from each of them. Okay, state the appropriate hypotheses for a chi-square test for goodness of fit to determine whether your calculator's random number generator gives each digit an equal chance of being generated. Then I have HO, each of the digits 0 through 9 for my random number generated is equally likely. HA, the digits are not equally likely. Carry out a test at the alpha equals 0.05 significance level. Plan, perform a chi-square test for goodness of fit. Random, I have a randomly generated sample. Independent, each digit is inherently independent because digits don't know the digit that came that came before. Large counts, NPs. 1/10 is your probability and your n is 200. So 200 times 1/10 gives you 20. The expected counts are all 20, which is greater than 5. All conditions are met. Do. Chi-square is observed minus expected squared over expected for the first component, okay, and then for the second component, and so on. And I get a 5.5. My p-value is 0.79, degree of freedom is 9. Because my p-value of 0.79 is greater than alpha equals 0.05, I failed to reject HO. I did not find convincing evidence that the distribution of values 0 through 9 generated by RANDINT is not evenly distributed or is not uniform. I have had students, though, that they've gotten this to fail. So they've gotten their random digit generator to show them that, or I'm sorry, they've gotten results that show that their random digit generator is not just giving equally distributed digits, which I think is totally fun because it's like one of those things like I broke math. But so it's I would just reason that out that still 200 digits is a short run of digits, and that the random digit generator is working properly. They're just by chance variation getting a unique distribution of runs in some of their digits, okay, and getting too many of some of those digits in, and it's causing the chi-square value that's giving them a reject. But remember that in the distribution of all the types of samples that we can get, that's kind of like a type 1 error where we reject HO and we shouldn't have, and that type 1 errors happen 0.05% of the time. So if I have a class of 20 students that do this, then one of my students should get a reject just by probability alone, okay? Because 0.05% of my distributions should fail. Okay, anyway, of my true distributions, like my distributions where HO is true, where I do have a properly working random digit generator. 0.05 of those distributions should fail. Okay, for part C and D, assume your random digit generator is working properly. What is the probability that a student who does this exercise will make a type 1 error? Probability of a type 1 error is alpha equals 0.05. Suppose that 25 students in an AP Statistics class independently do this exercise for homework. Find the probability that at least one of them makes a type 1 error. That's 1 minus the probability that we don't get any type 1 errors according to our probability chapter. Okay, the probability of at least one is 1 minus the probability of none. So the probability of none is 0.95, the opposite of a probability of 1. Okay, and then all 25 of us not making a type 1 error. Okay, then 1 minus that to find the probability of at least one type 1 error, and that's 0.723. Okay. All right, then the last example is of 2003 AP Stats for response question. Contestants in a game show spin a wheel like one shown in the figure above. Each of our 4 outcomes on the wheel is equally likely, and the outcomes are independent from one spin to the next. Okay. The contestant spins the wheel. If the result is a skunk, no money is won and the contestant's turn is finished. If the result is a number, the corresponding amount on dollars is 1. The contestant can then stop those winnings and can choose to spin again, and his turn continue, and his or her turn continues. If the contestant spins again and the result is a skunk, all the money earned on the turn is lost and the turn ends. The contestant may continue adding to his or her winnings until he or she chooses to stop or until a spin results in a skunk. What is the probability that the result will be a number on all the first 3 spins of the wheel? Suppose a contestant has earned $800. I'll just do A. On all 3 spins of the wheel, it's 3/4 each time, so we get 0.422, that you get this exact outcome of a spin with a number, followed by a spin with a number, followed by a spin with a number. Suppose a contestant has earned $800 in his or her first 3 spins and chooses to spin the wheel again. What is the expected value of his or her total winnings for the 4 spins? So the expected value is 0.25 times 0 plus 0.25 times 900 plus 0.25 times 1300 plus 0.25 times 1000, because you have 0.25 of each of the 4 outcomes after 3 wins resulting in $800. Now, you have 0.25 chance of just getting a 0 because you have $0 because you get the skunk. 0.25 chance that you get the 100, but the 100 will give you 900 total. You also have 0.25 that it lands on the 200, but that means that you would get, there it is, 200 plus 800, which is 1,000. And you also have 0.25 chance that it lands on the 500, which is 500 plus 800, which is 1,300. So the expected value is all these parts added up, each xi, pi, and you get 800. Okay. State, we wish to test HO, all 4 outcomes from spinning the wheel are equally likely versus, here's the question. A contestant who lost at this game alleges that the wheel is not fair. In order to check the fairness of the wheel, data in the table below were collected for 100 spins of the wheel. So here's actually 100 spins results. Based on the data, can you conclude that the 4 outcomes in the wheel are not equally likely? Give appropriate statistical evidence to support your answer. We wish to test HO, all 4 outcomes from spinning the wheel are equally likely, versus HA, at least 2 of the 4 outcomes are not equally likely. Tested output equals 0.05. Plan, perform a chi-square goodness of fit test. That's our inference method. Random, consider each spin a random outcome. Independent, prompt says that the spins are independent. The wheel has no memory. It's a chance device. Large counts is the sample size times the probability, which gives us 25. All expected counts are 25. All conditions are met. So we make a table of expected counts, which is right here, and then observed minus expected squared over expected gives us these components for the chi-square, that one being the largest, giving us 4.24, p-value of 0.24, degree of freedom 3. Because our p-value is greater than alpha, we fail to reject HO. There is not convincing evidence that all 4 outcomes on the wheel are not equally likely. Good luck. That's it for goodness of fit tests. All right, I'll see you again for the next 2 chi-square tests.